In this video, we will talk about how to graph general planes. So recall that a linear function f has the form. So first, if my function is in terms of one variable, it would have the form f of x equals a naught plus a1x, where the a naught and the a1 are just some constants. And if we replace f of x with a y, we could write this as y equals a naught plus a1x. And we've seen what the graphs of functions like this look like. These are lines. And the variables in the equation of this line are, there's the input variable, which was the x. And the output we're calling y. Okay, so now if we take a linear function that has more than one input variable, let's say it has two variables in the function, that would look something like f of x comma y, so there's an x and a y being inputted, equals a naught plus a1x plus a2y. And we could also rewrite this in the same way we did the function above. We'll replace the f of x comma y with a new variable like z, and get z equals a naught plus a1x plus a2y. So when you go one variable higher like that, one more variable, the graph is going to be one dimension higher. So it turns out that this graph is going to be a plane, because a plane in some sense is one dimension up from a line. And the variables in this equation, the input variables were x and y, and the output we called z. And we could keep going like this. So if my function was in terms of n variables, it would have the form f of x1, comma, dot, 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 comma, xn. And its equation would be something like a naught plus a1x1 plus a2x2 plus dot, 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 plus anxn. And this graph we call a hyperplane. And hyperplanes we cannot visualize in higher than 3 dimensions. We can't visualize in higher than 3 dimensions. So stuff that's in 3 dimensions or lower, we can visualize them and try to graph them, but not in stuff that's higher than 3 dimensions. All right, so I want to talk about an intuitive reason for the shape of why this second equation that we wrote down, the second form, where the input had an x and a y, why that's a plane. So if there's one input variable and my function is f of x equals a naught plus a1x, well, that graph is a straight line. So based off of that, we might expect that higher dimensional versions of this would also have straight, flat shapes. So what does straight look like in each of these dimensions? Well, a 2-dimensional version of a straight, flat graph is a line. A 3-dimensional version of straight or flat is a plane. And 4-dimensional or higher, so 4+ dimensional, we can't visualize, but we call these hyperplanes. All right, let's look at an example. So in this example, I want to graph this equation in 3-dimensional space. So the first thing that we can note about this is that this is linear. So one of the ways that we can see that is, if we were to rearrange the terms to get the z by itself, we would get 4z equals, moving the negative 24 to the right, we get positive 24. Moving 2x over, we get minus 2x. And moving negative 6y over, we get plus 6y. Then I could divide by 4 to isolate z and get z equals 24 divided by 4 is 6. And then minus 2 over 4x plus 6 over 4y. And then we can relabel the z as f of x comma y. And now this function has that linear form. So the way I could have recognized that from the beginning without having to rearrange stuff like this is to notice that with each of these x and the y and the z terms, their power is just 1. Like this is just x to the 1, and that's just y to the 1. So we don't have things like x squared or square roots or things like these variables in the denominator or the variables being multiplied together. That's the way I can see just by looking at it that this is linear. This means that its graph, since we're in 3 dimensions, is a plane. So the way I'm going to begin to draw this graph is by finding the intercepts. If I can find the intercepts, I can connect them and start to get a feel for what the shape looks like. Okay, so I'm going to zoom it out a little bit so I can still see the original equation. So let's begin with the x-intercept, and then we'll get to the y-intercept. And then finally I'll do the z-intercept, but it doesn't matter what order I do them in. So for the x-intercept, I'm going to draw a picture to help me remember, well, how do we find these intercepts? So I'll have my x-axis, my z-axis, my y-axis. And let's draw the negative directions, the negative y direction, the negative z direction straight down, negative x direction sort of going back into the page. So if I look at a point on the x-axis, and let's say that this is where the x-intercept is. So at that x-intercept, notice that the y and the z coordinates at that point are both 0. So y equals 0 and z equals 0. And that's going to be the key to finding the x-intercept. We are going to set those other coordinates equal to 0. So we'll set y equal to 0 and z equal to 0. Plugging those into our equation, we get 2x minus 6 times 0. That's plugging in for the y. Plus 4 times 0. That's plugging in 0 for the z. And I'm going to move minus 24 over to the right. So this equals 24. So we get 2x equals 24, and dividing by 2, x equals 12. And my x-intercept is a point, so I need to write it as a point and write all of its coordinates. So the x-intercept, its x-coordinate is 12, and the other coordinates are both 0. So 0 and another 0. So that's my x-intercept. Let's get the y-intercept. For that one, we set the other coordinates equal to 0. So x is going to be equal to 0, and z is going to be equal to 0. And if we plug those in, we get 2 times 0 minus 6y plus 4 times 0 equals 24. So this is negative 6y equals 24. And dividing by negative 6, we get y equals negative 4. So I could write down my y-intercept as a point now. So the x-coordinate is 0. The y-coordinate is negative 4. Z-coordinate is 0. And that's my y-intercept. So next we're ready for the z-intercept. So let's set the other coordinates equal to 0. So x equal to 0 and y equal to 0. That'll give us 2 times x minus 6 times y, plugging in 0 for both of them, plus 4z equals 24. And now if I simplify this and divide by 4, we get z equals 6. So my z-intercept as a point is 0, 0, z-coordinate is 6. So we have all of the intercepts. Now let's use the intercepts to help graph the plane. So I'm going to draw our axes. So z-axis straight up. The x-axis I draw slanted to indicate it's coming out of the page. The y-axis to the right. Negative y to the left. Negative z straight down. Negative x coming back into the page. And let's label the intercepts. So the x-intercept was at 12, 0, 0. The z-intercept was at 0, 0, 6. So the z-intercept is not as high away from the origin as the x-intercept is. Okay, and then the y-intercept was 0, -4, 0. And now I'm going to connect these. So I'm going to connect these with straight lines. And what that does is it forms this triangular shape. And I'm going to shade in that triangle. It makes this triangular shape. So the plane that this forms contains this triangle. So imagine you have this triangle, and this extends infinitely. So these lines would extend infinitely. So that's something we have to visualize. And to help us visualize it a bit better, I'm going to show this on GeoGebra. All right, so here is GeoGebra. I'm going to plug in my equation as an input. It's 2x minus 6y plus 4z equals, moving the 24 over equals 24. And if I look at this graph, I can see it looks like it's crossing -4 here. So that means that this is the y-axis, this green one, which means my axes seem to be sort of rotated. The red one seems to be the positive x-axis. In fact, I see these are positive numbers like 1 and 2 and 3. The positive numbers on this green axis are over here actually, like 1, 2, 3. So if you click on the picture and you drag it, you can rotate it. So if I rotate it, I start to get something like this. And I can't even see actually where this is intersecting the x-axis. So if you hover your mouse, you can zoom out. So I'm zooming out. And if I zoom out enough, I can see that x-intercept. I can see, oh yeah, it looks like it's crossing there somewhere at 12. And now I can click and rotate my picture a little bit, and I can see, yeah, this is that plane that we claimed we had. So GeoGebra can be a nice tool to confirm our answers, but I mostly care about, do you understand how we can reach that graph using the work that we did, really breaking down the concepts that we've talked about, in this case of intercepts and being able to plot 3D points. Okay, so what if we needed to graph more complicated shapes? We can describe those more complicated 3D graphs with what are called level curves and slices, which I'll also refer to as cross sections. So we will talk about these in the next video.